So today we are going to talk about scatter plots and correlation versus causation. These are really good things to know how to interpret for a standardized test. I see a lot of this kind of stuff on standardized tests. So, first thing we're going to do is just simply practice making a scatter plot. Do you guys know what a scatter plot is? What does it kind of look like? Exactly, it's a whole bunch of dots everywhere. Sometimes it kind of looks like there's a bit of a pattern going on. Sometimes it's just like a mashup of different points. So let's see what this looks like. We are going to plot all these points. So remember, each one of these is a coordinate point. So this is 0, 2. So to plot that from your origin, if x is 0, do you need to go left or right at all? Nope, but y is 2, so we just go up 2. So we put a dot at 0, 2. So that's just up 2. Then 2, 3. From your origin, that's right 2, and then up 3. So 2, 3. We writing this down? Jaden, stay awake. You're complaining that you didn't know what was happening the last couple days, but we got to stay awake today then. 4, 5. That's right 4, up 5. 6, 5. From the origin, that's right 6, up 5. Did that sound nice? Huh? No, it's not going to be a perfect line. That's part of the point. I'll talk about that in a second. And then 8, 8 from the origin, that's right 8, up 8. And then 10, 9 from the origin, that's right 10, up 9. Oh, you're right. I put it in the wrong spot. Thanks for telling me. That should be right. I think that's when I choked. That should be right 6, up 5. There we go. That looks better. Okay. Now, Alex pointed out he thought it was going to be a straight line, right? And is it? No, and that's okay. That happens a lot in a scatter plot. But don't you notice aren't your points all kind of going up and to the right? So this is not a perfectly straight line. I could not connect these points with a nice straight line. But what we call this kind of has like a bit of a trend, right? It's going up and to the right. Asia? Sure. What do you think we do for something like this? Yeah, we use on this, we call it a line of best fit. That's actually what we're going to do tomorrow. Today we're going to talk about the basics of what a scatter plot is, what the different relationships are, and then tomorrow we're going to draw the line of best fit. Now the purpose of this is actually very relevant because most things in the world, are they going to be like a perfect upward trend or a perfect downward trend? No, this is what real life data looks like, right? If you work for a company and you're collecting data for them or whatever it is you're doing, this is what your data is probably going to look like. Obviously, it can vary a lot, but it's not going to be a nice, perfect straight line. That is not how the world works, right? Things are going to vary a little bit. But when they vary a little bit, there still might be a trend, right? We still might be able to kind of represent it a little bit with a line, and that's what we'll do tomorrow. So this is what a scatter plot in general looks like. This one goes up and to the right. So what a scatter plot is, it is a graph that shows the relationship between two data sets. So maybe the number of coats sold versus the temperature outside. Maybe the amount of rain fall versus the amount of snowfall. I don't know. It could be really anything, right? Anything that can be represented with numbers. So the number of hours you work versus how much money you make, right? Anything that can be represented numerically, as long as you have two things, you can compare them in a scatter plot. So the first thing we're going to do is just practice reading a scatter plot. So example 1, the scatter plot shows the amount X in grams of sugar and the number of calories, the numbers Y of calories in 10 smoothies. So if you look at this graph, I'm going to zoom in on this a bit so we can talk about it. Couple things to notice. The bottom is labeled as sugar. That's our x-axis, so grams of sugar. The y-axis is the calories. And then you notice down here, see this weird little like squiggle? It looks like your graph kind of like had a spasm. Alex, you have a question? Oh, yeah, hold on to that thought. To take a look at this bottom corner, see how your graph kind of looks like it had a spasm? Does anyone know what that is? Yeah, it's called a break in your graph. It's when you have a really big set of data, but you don't need all that room. They do a break in the graph, which allows you to skip a big set of numbers at the beginning. We try to avoid that because it can kind of like make your data look a little funny, but that's what that is here. It's what allows. So it just represents that there's like a break in the data. So like it doesn't go, because see here on the y-axis how it goes from 0 to 240, but then it goes up by 10 each time. That's it indicating to you like, hey, there's a bunch of like things missing right here. So you don't have to start at 0 all the way up to there, right? Then all your data is going to be all the way up here and you're going to need this giant graph. So it helps like avoid that. All right, so part A says how many calories are in the smoothie that contains 56 grams of sugar? Alex, you said you knew? Yeah, it is 270. So to figure this out, you want to know the number of calories. So you go to 56 grams of sugar, which would be right here between 54 and 58, and go up, and then you hit this point, go over, that's 270. Good. So that would be 270 calories, and I'm just going to abbreviate as cal. How many grams of sugar are in the smoothie that contains 320 calories? So this one you go backwards, find 320 calories, and then go down and over. Asia? 70 grams. Yeah, 270 is right here. Go over. I'm sorry, I read the number wrong. 320 is up here. Go over, and then down, that's where they're seeing that 70. So 70 grams. Good. What tends to happen to the number of calories as the number of grams of sugar increases? You guys notice anything happening with your points here, Asia? Yeah, if you take a look, as the amount of sugar increases, in general, don't the number of calories increase? And think about what you know just in general, right? About like sugar versus calories. Aren't higher sugar things normally more calories? So that's reasonably logical, right? So how we write this is the number of calories increases as the grams of sugar increases. And there's a few different ways you can write that. This is just one example. You could say the calories go up as the sugar goes up, right? You can use some different phrasing there if you want. But in general, the number of calories increases as the grams of sugar increases. Yeah, it's a lot of sugar. A lot of things have a lot of sugar that you wouldn't think have so much sugar. These are some high sugar smoothies. These are not health smoothies. All right. Yeah. All right. So the scatter plot shows the hard drive capacities in gigabytes and the prices in dollars of 10 laptops. So very similar idea here. We have our hard drive capacity in gigabytes along the bottom, our price in dollars along the top. So what is the price of a laptop with a hard drive capacity of 8 gigabytes? Somebody I haven't heard from yet. What do you think? Annalise? Yeah, exactly. It's right in between, right? That 1,000 and 1,200. So what you do, go to 8 gigabytes, go up. That's right in between there. So that would be $1,100. These are some fancy laptops. MacBook Pros. What is the hard drive capacity of the $1,200 laptop? Somebody I haven't heard from yet. What is the hard drive capacity of the $1,200 laptop? Or someone at home, it doesn't have to be someone in front of me. Jake? Yeah, 12. Yeah, you go over to the 1,200, right? And then down, that hits at 12 gigabytes. And you can abbreviate that as 12 gigs is how you would abbreviate that. All right. And then take a look at this one. What tends to happen to the price as the hard drive capacity increases? What are you guys seeing? You seeing a trend? Change it up. I haven't had to say that in so long. What tends to happen? Asia? Yeah. Which again, think about it logically. If you have a computer with more features, right? More memory, more hard drive capacity, all those things, isn't it going to be more expensive? Yeah, good. So we would say the price increases. As the hard drive capacity increases. People at home, any questions yet? Oh, my handwriting is not looking so good, but I think it's reasonably legible at least. People at home, are we awake? Are we conscious? Okay. I worry when I don't hear from anybody. All right, onward. That side was really easy, right? Actually, this whole set of notes is really easy, so that way we have time to start our activity. All right, so on to the back. Identifying correlations between data sets. A correlation, it sounds like a big fancy word, but in general, it's not too bad of a concept. A correlation is simply a relationship between the data sets. Now, in the first two examples that we just did, wasn't there a relationship? A pretty clear one, right? As that hard drive capacity increased, you could very easily see that price increased. As the amount of sugar increased, you could very easily see that the calories increased. Now, is everything going to have like a nice relationship though? Not always, because again, a scatter plot can be of anything. Any two things that have number data, you can put in a scatter plot. If I wanted to talk about, the amount of peanut butter sold versus the amount of steaks sold, would those have numbers? Yeah. Could I plot it? Sure. Does it necessarily have anything to do with each other? No. Okay, so there could be things that you could plot that don't really have a clear relationship happening. Or maybe things have a little bit more of a vague relationship. Like, again, I don't know why I'm just thinking about food right now, but maybe like the amount of peanut butter sold versus the amount of jelly sold. Could that have a relationship? It could. Is it necessarily going to be like a super strong relationship? No, but could it like have some, like maybe people buy both at the same time because they're making peanut butter and jellies, but maybe some people don't. So it could have a strong relationship, but it doesn't have to, or it could just be nothing at all. You never know. Like steaks and peanut butter. Please don't buy those together for the same dish. Unless you're making Asian food, maybe. Like pad thai. That could be interesting. A peanut butter sauce, like a peanut sauce, if you're doing like a stir fry, that could be good. Yeah. All right, so there are 3 different kinds of correlations. There are positive correlations, that's that both increase at the same time. That's what we just saw. There's a negative correlation, which means X increases while Y decreases, and then no correlation at all. So we've seen some good examples of positive. No correlation means that there's just really nothing happening with them. There's not a clear relationship. Negative correlation could maybe be like the price of something decreasing. Like think like the value of a car. The longer you have a car, doesn't its value go down? In most cases, right? Exactly. Not 100% all the time if it's like a specialty thing, right? But most of the time it's going to decrease. That could be a good example of a negative correlation, right? Number of years you have a car versus the value of the car. So what we're going to just do is take a look at some patterns here and decide if it's positive, negative, or no correlation. So age and vehicles owned, that means your age. Your age and the number of vehicles you've owned. Now, don't take a look at what you think it would be. Take a look at the actual data plotted. Does that look like it has any relationship? Yeah, good, Brooklyn. I would say no correlation for this one. No correlation. Now, for this one, depending on who you asked, could there be a correlation? Yeah, depending on who you asked for sure. But, you know, there's some, like, look at this data. There's some 20-year-olds who have had 4 cars. And there's some 50-year-olds who have had, and there's some 40-year-olds who have only had 2, right? Maybe some person got into more accidents. Maybe one person can afford more cars than the other person, right? So it could vary depending on who you ask. But in this situation, there was none. Temperature and coat sales. Average daily temperature and coat sales. Are we seeing a correlation here? Which kind? Positive or negative? Negative. Good, Brooklyn. Yes, this is a negative correlation. Now let's talk about why this would be negative. As the temperature goes up, aren't less winter coats likely to be sold? Yeah. Again, could depend on where you're at, right? Maybe it could vary. Sometimes maybe there's a big sale, right? So it's not going to be perfect, but in general, this looks like a negative correlation. And then last one, we've already looked at this one, but that's okay. Hard drive capacity and the price of a laptop. Positive correlation, good. Okay. Not too bad so far, right? Okay. All right, so now let's take a look at correlation and causation. And instead of looking at graphs, we're gonna like read a situation. So remember, a correlation is simply a relationship. So that's just saying a relationship could exist. Like selling the amount of peanut butter sold versus the amount of jelly sold. There could be a relationship there, right? Those things could maybe have something to do with each other. But then causation, think of causation. What word does that really sound like? Cause. This means one actually makes the other happen. So that is when a change in one variable causes a change in another variable. Causation produces a strong correlation. For example, also like a strong correlation means you can clearly see, oh yeah, this is trending upward, right? This is positive or this is negative. Now, is it possible for something to have a relationship, but one not necessarily cause the other? I keep going back to my peanut butter and jelly example. I must want a peanut butter. You know what? I have peanut butter in my breakfast, so I think that must be what it is. It's just the only thing I can think about. It's also, I don't know, it's the only good example that's popping into my head. So 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 again, amount of peanut butter sold, amount of jelly sold. Could there be a relationship? Sure. But does someone buying peanut butter necessarily cause them to buy jelly or vice versa? No, you could buy one and not buy the other, right? There could be a relationship, but one is not causing the other to happen. Whereas if you look at like the temperature in coat sales, that definitely has a relationship, right? That has a correlation. Could this also be an example of causation? Is the temperature going up maybe causing less people to buy coats? That's definitely possible. If you look at hard drive capacity, right, versus the price, definitely a relationship. And it also has causation because that hard drive capacity going up actually makes the value of the computer increase at the exact same time. Okay, so some of these are, I think I changed a few of them from last year, so let's see. Now, we got to think about these again. Things can have a relationship, but one doesn't necessarily cause the other, so we're going to examine that. So example 3 says, tell whether a correlation is likely in the situation. If so, tell whether there is a causal relationship. That means first we're going to decide, is a relationship possible? Then we're going to decide, does one actually make the other happen? So the number of banks and the population of a city, do you think that could have a relationship? Yes. I would say for sure, yes. This could definitely have a correlation. Now, my next question to you would be, does the number of banks increasing necessarily cause the population of a city to increase? No, not necessarily. Now, if you think about it the other way, could the population increasing maybe cause the amount of banks to increase? Maybe. Yeah, so, but I would say with this one, like, sure, there's a relationship. Yes, Bailey. That's also possible. This is one that I would say there's a relationship, but one doesn't necessarily make the other happen, right? There being more banks doesn't make the population increase. And the population going up doesn't necessarily force them to build more banks. So I would say this is correlation, but not causation. And ones that we put on the test, I'll make sure they're very clear one way or the other, because there's some that could be like argued about a little bit, you know? The amount of time spent talking on a cell phone and the remaining battery life, does that have a relationship? Absolutely. So this definitely has correlation. Does this also have causation? Does one cause the other? Absolutely, because doesn't talking on your phone drain the battery? That literally causes it, right? So this is correlation and causation. Good. That's a good example of one where like one definitely makes the other happen. Okay, the number of people with brown eyes in the class and the average grade. Is there a relationship there? No. I would say this is no correlation. Right, your eye color has nothing to do with your grade. And then the last one, this one always throws people a little bit, so we'll talk about this one. The height of a toddler and the size of the toddler's vocabulary. Would you say this has a potential relationship? So think about as you get taller, do you possibly get older? As you get older, does your vocabulary possibly increase? Yeah, so I would say there could be a relationship there. But does you getting taller necessarily automatically increase your vocabulary? No. So this is another example of what I would say is correlation, but not causation, right? There could be a relationship, right? As you get older, you get taller, your vocabulary increases. A relationship's possible, but you being tall doesn't necessarily increase your vocabulary. So I would say correlation, not causation. Oh, how old is she? Cute. That's a cute age. All right. And that's it for notes.